The objective of this video is to introduce transfer functions and the hidden implicit assumptions that are required to apply linear control techniques to power electronics. The idea is that we want to be able to actively regulate our output voltage of our converters. We've previously talked about the notion of regulation, of line regulation and load regulation, where we talked about changes in output voltage due to changes in our line voltage, or changes in output voltage due to changes in our loading condition. That is, if our effective load resistance suddenly changes and our output current varies, our load voltage may vary as well. Now, we want to talk about how you actually design feedback regulators to monitor and adjust your duty ratio of your converter in order to maintain a constant output voltage in light of whatever disturbances may occur, whether this is a change of load resistance or a change of input voltage or who knows what. And the idea here is that we need to be able to know how to vary the inputs to our circuit, and in power electronic converters we're talking about the duty ratio of our active devices, and we need to know how to vary the inputs, not only how much to vary them but also how fast to vary them. So our notions, the terminology that we defined around regulation is no longer sufficient. Yes, we know that we want to drive this to 0% regulation. We want no error in a steady state sense. But now we need to start talking about how fast you vary your inputs and how much you vary them. So if you're talking about your duty ratio, you could liken this to learning to drive a car, where you got the feel for how to use the accelerator, the foot pedal, to accelerate your car. When you first drove a car, you were probably fairly aggressive with it, or maybe you were fairly hesitant with it. So if you push your accelerator too hard in response to a desire to change the speed of your car, you suddenly go way too fast, and then you suddenly back off your accelerator and your car lurches to a stop, right? And so the art of designing feedback regulators is knowing how aggressive you should be with your accelerator, how much you should change your duty ratio given the current circuit operating conditions, so as to avoid overshoot. When you lurched past your desired speed, when everybody leaned back in their car seats because the car accelerated too fast, that was an overshoot situation. And then when suddenly everybody was pushed forward into their seatbelts because you took your foot off the accelerator too quickly, that was undershoot. And this looks like ringing on an oscilloscope. If you were to look at a graph of your output voltage versus time, and you have overshoot and undershoot taking place, you'll see that there's some oscillation of the output voltage. So we want to avoid that. And what this lecture is about is setting up the framework, starting to set the stage for us to delve into linear control techniques as applied to power electronics. And in some ways, this should be a review from your previous classes, such as ECE 330 and 342. But when you apply these techniques to power electronics, it looks a bit different than you've previously experienced. So we're going to start by talking about transfer functions and the assumptions that are made when we consider transfer functions. And then in later videos, we'll work up to ways that we can visualize transfer functions and using Bode plots and poles and zeros. We're going to be studying frequency response transfer functions. Using small signal analysis techniques. And when we say small signal analysis, what do we mean? We mean that we're going to be studying sinusoidal inputs to our system and observing the output that results. And we choose sinusoidal inputs. We define all of our inputs as being a sinusoid at a certain frequency because sinusoid functions are infinitely smooth. You can always differentiate them, you can always integrate them, there's no discontinuities. So unlike on this slide right now, I've shown you a graph of what our inductor current looks like. You can see it's a triangle wave, and if we were to differentiate it, we get a square wave up above. These functions are more complicated because when you differentiate them or integrate them, they become a different function. If you differentiate or integrate a sinusoid, it remains a sinusoid but is phase shifted to become a cosine or back to become a negative sine, for example. So this property of being infinitely smooth is very important, and it enables a lot of linear analysis techniques that we're going to be using in this class. And the other reason that we like sinusoids is that we can take any arbitrary waveform and decompose it into a sum of sinusoids. Fourier showed us this. So this is the Fourier series, or the Fourier transformation. So sinusoids become this general purpose function, and if we can quantify a system's response to a sinusoidal input, we can generalize what its response would be to any type of input. Also implied in this is the assumption that we're going to have periodic conditions. So if we're going to be studying sinusoids, we need our excitations to be considered as periodic. This type of analysis also requires linearity. And what does it mean for the system to be linear? Well, it means that we can get proportional responses. So if we have a linear system and we were, for example, to be looking at our output voltage in response to changes in our input voltage, a linear system will behave so that if we change our input voltage by 5%, the output voltage will change by 5% as well. Or if we double our input voltage, our output voltage will double. And we can see that this is true when we study the output voltage relationship for a boost converter. If we change our input voltage by a certain percent, our output voltage will change proportionally. If we double our input voltage, our output voltage will double, if everything else is held constant. However, you can see that this is not true if we consider the relationship between the output voltage and the duty ratio. Since our output voltage depends on the duty ratio as 1 over 1 minus d, we have a nonlinear relationship. If we were to change our duty ratio by x%, our output voltage will not change by x%, it will change by something else. And we can depict this by actually graphing our relationship here. So on the y-axis, I'm going to place our output voltage, and on the x-axis, I'll place the duty ratio and assume that our input voltage is fixed at some Vin value. When our duty ratio is 0, Vout is equal to 1 over 1 times Vin, or it's just equal to Vin. And as d increases, the output voltage will rise towards infinity. So we'll see some kind of trend like this. So what to do here? We have a system that is nonlinear between the critical input of the system, which is our duty ratio, and the output of our system. Yet our control framework that we're going to be using requires a linear system. The answer is that we linearize the system. We realize that we're going to nominally be operating our boost converter about a certain operating point. Perhaps we will always be outputting 48 volts when our input voltage is 12 volts. And we can say that, well, we want our duty ratio to be at this point over here. And we can figure that if we approximate this curve by its tangent, we get some kind of line that looks like this. And we can figure that within some reasonable bounds here, we have an approximately linearized system. We have an approximate linear relationship. So if we change our duty ratio by small increments about its nominal operating point, which is this point right here, our system behaves approximately linear. This is not completely the truth, it's an approximation. And we'll be talking about that more in later videos. So what else does linear mean? Linear means proportional. It also means that we can use superposition. It means that we can look at a system that is operating at nominal conditions, and we can add to its input some delta D amount, and we can study that by considering two separate systems. We could study one system that just has an input varying by delta D, and another system that is at its nominal condition, and sum the response of the two. So this should be a familiar concept to you from your linear circuits courses. You've previously learned that a technique to solve a circuit that consists of multiple voltage sources is to use superposition, where you solve the circuit once for each voltage source, where that voltage source is turned on but the other voltage sources are turned off, and then you sum up the resulting currents in order to get the final circuit solution. So that was using superposition, and we'll be able to use that same technique in the types of systems that we're describing. In fact, this enables us to be able to express our input to our system. Let's say we're talking about duty ratio as an input in terms of a nominal duty ratio plus some delta D of t. And this delta D of t is our small signal perturbation. This is our sinusoidal input that we previously discussed. Or similarly, we could write the input voltage to our system in terms of a nominal input voltage plus some delta Vin of t, which is again our small signal. The other implicit assumption that we're making in this type of analysis is to assume that our control action is slow compared to our switching frequency. So on the left side, we've sketched what our pole voltage looks like as a function of time, and it's a square wave that is switching at the switching frequency of the converter. We're going to assume that we're operating our converter controller slow enough so that this voltage appears as its average value. So we don't take into account the dynamics of the switching frequency of the converter. We instead look at things as being in an average sense, but that average is allowed to move. So if we're switching at 100 kilohertz, maybe our duty ratio is allowed to vary at, say, 10 kilohertz, so 10 times slower. Let's now look at an example of what a transfer function can mean. Let's say that we have a power converter that I'm going to sketch as a black box. And as an input, our power converter takes a voltage in, and as an output, we have a voltage out. This could have been different quantities. We could have had an input be current, we could have had our output be current as well, our input could have been duty ratio. The point is that we're relating the output voltage to some input quantity. And we're going to talk about the transfer function for this block. So let's say that that Vn is a small signal perturbation, and we say that we're going to supply a Vn of 10 millivolts, and we'll supply it at a certain frequency. We'll supply it at 5 kilohertz. And then we have some measurement equipment on here, and we observe an output voltage of 50 millivolts, also at 5 kilohertz. So we can say that this transfer function is behaving like an amplifier because it amplifies our input voltage to a larger output voltage, and it has a gain equal to V out over V in, which in this case is 5. So 50 millivolts divided by 10 millivolts is 5. And this could have been a peak-to-peak value, it could have been an RMS value. The point is that since this is a linear system, you just have to use the same convention or same notation in regards to both the input and the output. So what do we mean when we say that we provided this small signal perturbation at 10 millivolts? It means that if we were to look at a graph of our input and output quantities, we would see that we have Vn as being some sinusoid, and this is at 10 millivolts and at 5 kilohertz. And we could graph V out on here, but we're missing a key piece of information. We know that V out is also a sinusoid at 5 kilohertz, but we haven't specified what phase it is relative to V in. So perhaps this transfer function had a gain of 5, but a phase delay of, let's say, 45 degrees. So in that case, we're going to see V out being a sinusoid that looks something like this, that's phase shifted in time. It's amplified and phase shifted in time from V in. So if this is V out, we're saying that it has a peak of 50 millivolts, and it has a phase delay from here to here of it has a phase delay of 45 degrees, or a phase shift of negative 45. So we say that our amplifier had a gain of 5 and a phase of negative 45 degrees. And so now we know what our transfer function is doing at this point, at this specific frequency. So the idea of a transfer function is that it relates an output, it represents an output divided by an input. And so, for example, this could be an output voltage divided by an input voltage. It could be an output voltage divided by a duty ratio. It could be an output voltage divided by an input current. It could be an output voltage divided by temperature. It could be an output current divided by an input current. It could be any two quantities of your system. It doesn't matter. You specify what they are when you define your transfer function. In most cases, in this class, we'll be looking at the output voltage divided by the duty ratio. So the transfer function is relating these two quantities, an output and an input, and it relates them in terms of gain and phase at a specific frequency. So it's a function of frequency, and it tells you the gain and phase of this of the relationship. So how much that output relationship will lag or lead the input quantity, and how much that output quantity will be larger or smaller than the input quantity. Because it's a linear system, the input and the output will always be at the same frequency. And when you talk about transfer functions, you can calculate these explicitly if you know your system well enough. So if you're talking about a circuit that's got resistors and inductors in it, you can presumably derive the impedance of the circuit and determine the transfer function of voltage to current or current to current or so on and so forth. But you can also measure these explicitly. So this is especially useful when we talk about power electronics. We can go back to our circuit at the top here, and we can apply variations in our duty ratio and then measure what the output does in response. So if our input changes X percent, we can see what percent our output changes. And then we can quantify this in terms of a transfer function. So we can sweep that variation in our input over some frequency range and observe the result of the output, and we can capture this within the transfer function. So the point is that you have two ways of determining your transfer function. The first is that you calculate it explicitly, and the second is that you measure it. And oftentimes you may do both to validate a system. Okay, so our transfer function gives us gain and phase information relating an output and an input over a frequency range. And when we talk about power electronics, we have a certain convention for how we express these quantities. We always express gain in decibels, which you can calculate using 20 log times your unitless gain. So if you're expressing, as in our previous example, we had an output of 50 millivolts for an input of 10 millivolts, and we found that gave us a gain of 5. For our class, when we're talking about power electronics, we're going to take 20 times the log of 5 to get our gain in decibels. And we express this in units of decibels. Sometimes it's helpful to call the quantity decibels volts, or decibels amps, or decibel ohm. So decibel ohm, for example, could be if you're taking an output over an input current. Decibel amp could be if you're taking an output current to an input current. And decibel volt would be a volt to volt, the decibel version of a volt to volt gain. So the reason that we do this, the reason that we convert our gains into decibels, is to facilitate a set of tools when it comes to plotting the frequency response of these. It helps with Bode plots. It allows us to add transfer functions, subtract transfer functions, divide and multiply transfer functions in certain ways that are highly conducive to hand sketching and facilitating understanding. So for that reason, just historically, in power electronics, we expressed our transfer functions in units of decibels. For the same reason, we express our phase angle always in units of degrees, and we express our frequencies in hertz. So we don't use phase in radians, and we don't use frequency in radians per second. In power electronics, we're always working in decibels, degrees, and hertz. So now let's talk about an example of a transfer function for a circuit. Let's say that we're going to do small signal analysis of an LR circuit. And so what we're trying to do is establish a transfer function, the small signal transfer function, that relates our small signal output to our small signal input perturbation. This is the transfer function we're trying to find. And we can do this by directly studying the circuit that I've drawn here, but it's simpler for us to take advantage of superposition and break this up into a small signal AC equivalent circuit. And since superposition holds, we know that we can pull out our capital V in source, our DC source, and our capital V out results into its own separate circuit and just study the small signal perturbation. So that is, we can just study this equivalent circuit down below. And since we're talking about our input voltage being a sinusoid, we can directly go to the Laplace modeling of our circuit. Our inductor has an impedance of S times L, or in other words, it has an impedance of J omega times L, and our resistor has this nominal impedance of R. So we call this the small signal AC equivalent circuit. And at this point, we can easily calculate our output to input voltage relationship, which we can then convert into the frequency domain by using S is equal to J omega. And I said that we're going to be working not in radians per second, but rather in hertz, so let's write this explicitly as a function of frequency. And we now have a transfer function which we could express in polar form as consisting of a gain, which is a function of frequency, at an angle phi, which is a function of frequency. And as I said earlier, the gain and the phase are the two fundamental quantities that our transfer function provides us as a function of frequency. In later videos, we're going to be talking about techniques to visualize transfer functions and to manipulate and combine transfer functions. But this video has exposed you to the basic underlying principles and the framework, the terminology and the framework that's going to be necessary for us to move into this space and ultimately work towards designing closed-loop regulators for power electronic converters.